Then let's go to start with more one PDE seminar of the Universidad de Chile, DIM and CMM. It's a pleasure to introduce Professor Noemi David, de la Universidad de Lyon, that will talk to us on singular limits arising in mechanical models of tumor growth. Thank you, Professor Noemi.
Thank you. Thank you very much for the introduction, and thank you a lot for the invitation, particularly to Eugenia. It's a pleasure to be able to talk here today. So I will present you, in fact, two results. So actually the talk is going to be, in fact, sort of a union of two short talks together. So two results on two different singular limits that arise in some mechanical models of tumor growth, which consist of reaction and diffusion systems of PDE. So let me just introduce very quickly the models. Well, obviously, cancer growth is a very complex phenomenon, and so the mathematical modeling of cancer includes a large variety of different equations and systems. But what I will talk about today concern in particular those models that focus on the mechanical aspect of tumor growth, which is, I think, nowadays the most used approach to tumor growth. And this means, in fact, that we are going to look at the tissue or the tumor as, in fact, a fluid. So this is a macroscopic description. So we look at the tumor as a continuum, and we see it as a fluid that is, in fact, flowing into a porous medium, which would be the extracellular matrix of proteins in which the cells, tumor cells, are moving. Okay. So we look at the tumor as a fluid, and we want to describe the population density in space and time. And the first ingredient into the mechanical description of tumor growth is a notion of pressure. So there is a notion of pressure inside the tissue, inside the tumor, and this is, as usual, an increasing function of the density. And in particular, as I'm going to show you, the choice of the pressure law, and in particular the stiffness of the pressure law, helps distinguish compressible and incompressible models. And then, so this pressure has two main roles. So it controls the movement. And so we have a choice now to be made to define our model, which is the choice of the velocity pressure relation. So for instance, we can use Darcy law, which means that the velocity is minus the gradient of the pressure, and so we are describing the fact that cells move down pressure gradients. So they are moving from regions with a higher pressure towards regions where the congestion is lower, and essentially towards region where they have more space, the space that they need in order to divide. But in this way, we are only describing the friction between cells and the extracellular matrix, and not the friction among cells themselves. And to do this, we use Brinkman law, and we introduce this parameter nu, which represents the viscosity inside the tumor. Okay. And so we have these different choices, and then well, the second role of the pressure is also to control the proliferation itself, not only the movement. And this happens because essentially when the pressure is too high, cells are too packed, they can sense it, and so they stop the division. So the division is inhibited when the pressure is too high, and so the growth rate will be something like this. So this will be your G, where this is the homeostatic pressure, okay, and is a decreasing function of the pressure, and it is zero at the homeostatic level, okay. And so the goal of the talk would be to show you how towards singular limits we can link these different representation, these different models that we can build depending on the choice that we make, for example, for the velocity pressure relation or for the density pressure relation. So first of all, I will show you how to pass from Brinkman to Darcy towards the inviscid limit nu to 0, and then how to what is the incompressible limit from a Darcy model towards a free boundary problem. Okay. So let's start with the inviscid limit. So the system, the equation let's say that is the starting point is this one. So nu represents the density, the population density, and it evolves with a velocity field that is minus this gradient of W, where W solves the Brinkman law. Okay. And the reaction depends on n, where here, in fact, I didn't mention, but for this problem, I take a linear pressure. So this is supposed to be the pressure P, but I take it linear, so it's simply equal to the density, okay? So this is Brinkman law, and then I have a growth rate that depends on the density. And I want to show that when I take nu to 0, so I take the inviscid limit, I obtain Darcy again, because now the velocity field will be just minus the gradient of the density. Okay, so n0 will be the limit of my sequence nu. And so what is the problem? So why this is a singular limit? The reason is that I will pass from an equation that has a hyperbolic flavor. So this is, in fact, a transport equation where W is quite irregular. And I want to pass from this to an equation that is degenerate parabolic. This is, in fact, is a porous medium equation because this term, I can actually rewrite it as a Laplacian of a power. Okay, so this is a porous medium equation, is degenerate parabolic. And I know, for instance, that the solution to this will be quite regular. For instance, I have a BV regularity on the density. But for this, the original problem, the regularity on n is quite low, while I have a much higher regularity on the velocity field, which is the opposite for the porous medium equation, because, for instance, we know that the Laplacian of n for a porous medium equation is only a measure. The reason being that for the porous medium equation, you have completely supported solutions. So you have solutions of Barnblatt type, so of this form, that are completely supported, and where the gradient has a jump here. So the solution has a kink, the gradient has a jump, and so it's much less regular, the velocity field. And so I have this change in nature, which is why this is a challenging problem. And also, let me mention that this W can actually be written as the convolution between a kernel K and N, where K is the solution of the fundamental solution of this equation. So actually, when nu goes to 0, K converges to the Dirac delta. Okay, so this so this is actually what we expect to happen, that W converges to n0. Okay, because K converges to the Dirac, and K is something like, so K is something like this in 1D. Okay, this is K nu, and is converging to the Dirac as nu goes to 0. Okay, so you can also see this as a limit from a non-local diffusion equation to a local diffusion equation. Okay, and this actually was yes, let me just mention another thing, that we are going to look at systems. So we want to describe, for instance, the interaction between tumor tissue and healthy tissue. And so we have two species. We have N1 and 2, and the system is coupled in this way. So N is the total density, is the sum between N1 and 2, and W, so they both evolve with the same velocity field, where W solves Brinkman with the total population, and also the reaction depend on the total population. Okay, and I want to pass the limit in the system. And so let me mention that previous works on how we can approximate the porous medium through a no-local equation was initiated in 2001 by Lyons and Masgalik. And then there are recent works, for instance, this one by Carrillo, Esposito, and Hu, where essentially they are able to prove that the porous medium equation can be approximated through no local kernels. But in this case, and also in the other papers, the kernel is much more regular somehow, because our kernel has a singularity in fact at 0. Okay, so let me start with the visco-elastic system, so the Brinkmann system. We know already that a weak solution exists and is unique, which is a result by Thomas Dönbjerg and Markus Schmidtchen in 2021. And so, and we also know some information, some a priori bounds on the solution. Some of them uniformly new, and some of them depend on new. So, for instance, we know that both species are bounded in N infinity L1, but also in L infinity, where n bar here is the maximum level. So it's the 0 of the function G1, G2. Okay, is when the proliferation, the division is inhibited. And then we know that W is L infinity, L1, L infinity, also uniformly new. What we don't know to be uniform in new is the regularity on the derivative of W. Okay, so for instance, we have these two informations, but we don't know if they are uniform. Especially the second one won't be uniform, because we already know that in the limit, the Laplacian of n is just a measure, for instance. Okay, so but the goal is to prove that at least the fact that W is in L2 H1 in space is uniform in U. So this is the first goal, to prove that at least this information is also uniform in U, which will help to pass to the limit. So from what we already know, we can already extract subsequences that converge weakly, okay, for the species and the total density, and also for W. So this we have weak convergence. We also know that these limits are actually the same, okay? And the reason is that, well, W, you know, you can write W as the convolution between n and the kernel, and then you simply pass the convolution onto a test function, and you know that this converges strongly and converges weakly to a naught, okay? And so actually the weak limit of W is in fact a naught, okay? Okay, so this here I wrote the weak formulation. So this is the weak formulation of the problem at level nu, and we want to pass the limit and obtain this. So we have a couple of problems. So first of all, we need to upgrade the weak compactness of the density to strong compactness. The reason is that, for instance, here in the growth rate, so I didn't say this, what are the assumptions on G, I just said that so they are decreasing and they are C1. But in general, they are non-linear. And so we need strong compactness to pass to the limit in here. Okay. And then we want to show that actually the gradient of W converges strongly in L2. And the reason is that for this kind of systems, it's quite involved, and actually we don't know if it's possible to show or not, to infer strong compactness on the single species. Okay, so on N1 and 2. And the reason is that in this system, since the velocity field is the same for both species, you have a property of the preservation of segregation, which means that if you start from N1, for instance, like this. Okay, so this is the space, this is 1D, so this is N1 and this is N2 initially, okay? And then you let them evolve, they will divide and they will move. And in the end, and at some point, you will have actually a sharp interface. Sorry. You will actually have a sharp interface, okay? Because the two cannot mix. They cannot mix, so you will have, at some point, a sharp interface. And so you know already that you cannot hope for more than BV regularity for both species, okay? You surely will have a jump. And so probably something can be done in 1D, but in multi-D, we don't even know if they are actually BV. And so it is very involved to prove strong compactness on the single species. And that's why to pass to the limit in this term here, what we do, rather than show strong on this, we have weak on this, and so we will show strong compactness on the gradient, okay? Okay, so this is the main result, because everything is, sorry, this is the main result. So assuming something on the initial data, which is quite standard. So we need, for instance, control of the second moment initially, and everything uniform in U. Then we can show that N converges strongly, and that the gradient also converges strongly. Okay, and this is this result you can find in this paper with Thomas Dumbietz from the University of Warsaw, and Meinak Mandal and Marcus Mitchen from the University of Dresden. And this is something we did in collaboration with them. So the key result on which the inviscid limit is built is this entropy dissipation inequality. So what we want to show is, provided that all this is bounded initially, what we show is that this inequality holds where H is the usual Boltzmann entropy. Okay, so H is the Boltzmann entropy, and we can show that for NU, H at final time, capital T, minus H initial time, and then we have this dissipation term is less or equal than what comes from the reactions. Now I will explain how we obtain this the entropy dissipation and why it is important. So the proof is going to be actually quite formal, but the idea is that so first of all, we have propagation of the second moment control. So this kind is classic in this kind of equation, that if you control the second moment initially, then you will control it for all times. And this is also true uniformly in U, okay? And then if you can control the second moment like this, you can also control this term, so n times modulus of log, uniformly also in U. And this is important because, for instance, it gives you that in the end, this term will be controlled. Okay. So once we prove this, what we want to do is to compute the Boltzmann entropy along the flow. Okay, so we compute the time derivative of the Boltzmann entropy using the fact that N satisfies this equation. Okay, this is the equation of N, because when we sum the equation of N1 and 2, they have the same velocity field, and then the reaction is a bit less, it's not self-contained, but I will call it R for the sake of simplicity, okay? So this is the equation of N. So what I'm doing essentially is somehow I'm testing the equation against log of N in a formal way, okay? Because when I do dTh, then I obtain log minus 1 times dTn plus dTn. And so I have, I'm testing the equation against the log. And so from the divergence term, I will have a grad log here, dot n grad w. And then I have the reaction, okay? But from here, so this is a grad n over n, okay? So the n goes away, and then when I integrate by parts again, I will have n Laplacian of w. Okay, so I will have this term on the left-hand side. And when I integrate in time, I have from here this difference. Okay, so why do I have a less or equal? The reason is that all this is just formal, but I cannot test the equation against the log because my solution and nu doesn't have the necessary regularity for log n to be an admissible test function, right? So there is actually a rigorous argument which gives me this less or equal. And this is also something you may have already seen in different contexts because it's quite standard. So what we do is, since we want something that is a solution that is regular, so we can test against the log, we regularize the equations. We regularize the equation adding an epsilon Laplacian to both equations. Okay, now we have something that is uniform parabolic, and so we will have very nice solutions. And then we can actually test against the log, in particular log of n plus delta, so we are away from also from vacuum. And then we pass the limit, both parameters to 0. Okay, so just to give you the idea, so this is the regularized system. Okay, where actually is not really a system anymore because they're not coupled, because here, because here what I take as a velocity field is not regularized. Okay, this grad w, and also here the n, these are not regularized. These are the solution and the unique solution of my original system. So they exist, they are unique. I can take them and define this equation, okay, or on n1 epsilon nu and n2 epsilon nu, okay. But okay, so the important thing is that I have this regularization, and now I can do the same. I can define the Boltzmann entropy functional actually regularized, okay, and then I studied it along the flow, and this is rigorous. Okay, the only difference is now that everything is justified. This is rigorous, and so when you compute the Boltzmann entropy along the flow, this time you will have an extra term, this one that comes from epsilon Laplacian. When you test against the log, what you will have is this. So you have a grad n squared over n plus delta. So we cannot pass the limit epsilon to 0 in this integral because we don't have enough information, but it doesn't matter. This has a sign, okay, because it's a square, this has a sign, and I can throw it away. And this is why I have an inequality then in my original, in my final entropy inequality. Okay, so this is where the less or equal comes from, simply because I need to regularize. Okay. But okay, so finally I have this inequality. And so what does which information does this give me? So for instance, I finally can control the gradient of W squared, because this, I can rewrite it as a minus W Laplacian of W, okay? And then I use Brinkman law. Brinkman law was this one, so minus nu Laplacian of W plus W equal to N. I use it here, and now I have two terms. One is the one that I just bounded thanks to the entropy inequality, okay? And the other one is non-positive. Okay, so I can just throw this away, and this is controlled. And so what I'm saying is that the norm of the gradient in L2 is controlled by the term that I just, the dissipation term in the entropy inequality, okay? Because this is less or equal than 0, okay? So I have this bound, first implication. And then I also have that this, if I don't throw it away, but if I want to keep the information, this is controlled. So actually the the square root of nu times Laplacian is controlled in L2, L2. So this is another information. And then I also have a control on the time derivative of W, because you can use again the kernel representation and write it in this way. Then I use the equation on N here, and I have the path from the divergence from the transport part and the reaction. And they are both controlled because N is in L infinity, the gradient is in L2, this will be also in L2, and same here is controlled. And so I have a control of dTW in a negative Sobolev space, okay, in L2 H minus 1. And so combining this, and using Aubin-Lyon, then I have strong compactness, okay? I have strong compactness of W, 2 and naught. Then I have more because I have that, as I said, this is controlled. And so if I multiply it by another square root of nu, this will converge strongly to 0. So N, which is given by the Brinkmann law, is the sum of something that is converging strongly to a naught and something that is converging strongly to 0, which was not trivial because we don't have a control on the Laplacian of W. So we could not say that this, I mean, I can just ignore this if I didn't know that I also have this control, which also comes from the entropy inequality. Okay, so I have both W and N converging strongly to a naught, but still my gradient is converging only weakly. Okay, and this is enough to pass to the limit in the equation for the total density. The reason is that the total density is dt and nu equal to divergence of n nu grad W. And I have strong for N and weak for the gradient. And so this is enough. Not for the system, but for the total density it is. And so now the goal is to use this information. So to use the fact that I have an equation on the limit total density, okay? And I will use this to get the convergence, the strong convergence of the gradient. And how? So now I can, this is simply a porous medium equation, okay? So I can again compute the Boltzmann entropy of N naught, okay? And this time I will have an inequality because it's simply a porous medium equation. So I have enough regularity to actually have an equality, which is very important. And now what I want to do is to compare this equality to this inequality that I had before. By comparing, I mean that, so this term here, okay, is actually greater than the L2 norm of the gradient. This is what we had before. So this term, I know that is less or equal than the terms that comes from the entropy inequality. And then the other one that comes from the entropy equality, I just add them since they are in a way with a good signs in a way that the sum is 0, okay? That's why I need equal. And if I do that, I will have, so this, which is what I actually want to keep, okay, that comes from here. And then I have the difference of the corresponding terms. So I have this difference here, and this will be less or equal than 0, simply by assuming so. This is an assumption I didn't mention, but so I assume that the entropy initially at level nu are always less or equal than the final entropy, I mean the limit entropy. Then for this, at final time, I use the lower semi-continuity or convex functional, okay? So I can also show that this is less or equal than 0, okay? And for this one, I will show, I mean, I will not show you because I rather skip this technicality, but one can show that this actually converges to 0 when nu goes to 0. It's quite technical because we have strong compactness of N, but here we have a log. And obviously n can be 0. We want to allow the density to be equal to 0 somewhere, since we are, I mean, it's part of the modeling. And so it is a bit technical because we have a log, but we can show that this goes to 0. Okay, so finally, oh, sorry, somehow okay, maybe there's a slide missing, but okay, I will just conclude here. So this goes to 0. Okay, this one. These two are less or equal than 0. Okay, so it's essentially what you proved is that the lim sup of this norm, of the L2 norm of the gradient of W, is less or equal than the L2 norm of the gradient of N. And so you have upper semi-continuity and lower semi-continuity of the norms, which means that the norm of grad W, okay, even without the square, is converging to the norm of grad N. Okay, so I have weak convergence, I have a norm convergence, and I conclude strong convergence. Okay, and once I have this, I can also pass to the limit in the system. So the idea is really to use the fact that I can infer that I can pass to the limit in the total density equation, and then use that to get the compactness of the gradient. Okay, and a similar idea will also play a role in the incompressible limit. But let me just ask you, how long do I have still?
You have 20 minutes.
20?
Yes.
Okay, perfect. But interrupt me when if I'm too long. Okay, so let me just recap what we just saw. So using so passing to the limit nu to 0 in the Brinkmann model, we just saw that we can obtain a Darcy model like this one. But now what I want to show you is how we can pass to the incompressible limit, which is a different kind of singular limit, which is very used in tumor growth modeling. And so now my pressure will be a power of the density. And actually, very recently, the same strategy that we used with Thomas, Meinak, and Marcus for the linear pressure was adapted to power law pressure like this by Charles Bar and Jakub Trzaskowski to pass to the inviscid limit also there. So that works also for power laws. So once we have a Darcy problem with the power law, what we want to do is to take this exponent to infinity. And what this gives you, which is called incompressible limit, is a way to link a compressible model to a free boundary problem. Because in fact, what you will obtain is that the limit pressure and the limit density satisfy something like this. So in the limit, the pressure is no longer a function of the density, but is a graph. It belongs to a graph of the density. So in particular, if the pressure is positive, then the density will be constantly equal to 1. And instead, where the density is less than 1, the pressure will be 0. So let me just draw very quickly. So this will be your P, okay? This is P equal n to the gamma. When gamma becomes larger and larger, what it happens is something like this, okay? So as I said, in the limit, if P is positive, then n is equal to 1, which is something you can see here. And that's why we call it incompressible limit, because we have saturation, complete full saturation of the density in the positivity region, the positivity set of the pressure. And so you will have, in the end, a free boundary problem where this is the set P infinity positive, which is n infinity equal to 1. And this is a free boundary that is evolving with velocity equal to Darcy to minus the gradient, so Darcy law. Okay. So I will show you, in fact, how we can pass this to this limit. And so, as I said, we pass from a porous medium equation. This is a porous medium equation with coefficient gamma plus 1 to an incompressible free boundary problem, where omega is the positivity set of P. And in omega, the pressure satisfies an elliptic equation. So in fact, in the limit, in the positivity set, you have no density anymore because the density is 1. And in fact, you can see that if n is 1, then this goes away and you have Laplacian of P equal to minus G or this otherwise, okay? Which is something you can also see from the evolution equation on P. So P actually here, at level gamma, satisfies an evolution equation. You can compute it. This is the equation. And since you have a gamma here in front of this term, if you formally divide by gamma and pass to the limit gamma to infinity, well, what you will obtain is P times Laplacian plus G equal to 0, which means that this is equal to 0 where P is positive. Okay, so again, the same relation, which is also called complementarity relation. Okay. So, okay, this I will actually not spend much time on this, just to tell you this is a very this is a problem that actually has a very long history. I started with the classical porous medium equation, and then it was extended to tumor growth models in the seminal work by Bertam, Quiros, and Vasquez, and then adapted to many other models, but I will not spend the time to explain all of this. So let me just tell you what is the difficulty in passing to the incompressible limit. So in particular in systems. So this is the same system that we recovered from the Brinkmann with the inviscid limit, okay? And actually it was very involved problem to show even existence of a solution for this. Okay, the first result is by the Gviazdas and Pertam in 2019. And what they do to prove the existence of solutions is to show some stability estimates, which are, some stability estimates on the pressure. And in particular, they can show something on the gradient and on the time derivative of the gradient, using the fact that they can bound the Laplacian of the pressure. So as I said, this is a porous medium equation. And as always in porous medium equation, you can control the Laplacian of the pressure in L1. And this is sharp. But this works. And thanks to this, they can bound the time derivative of the gradient because, so essentially everything is bounded here. Everything is controlled. And then they have gamma P, which is again in an infinity, and this in L1 because they can prove it here. So you can see immediately what is the problem if one wants to pass to the incompressible limit. And the problem is here. So here you have a gamma, and here you have a gamma. Okay. So even if you can show this control uniformly in gamma, then when you want to take gamma to infinity, you have a big problem in the regularity here because this will explode. Okay. And so because this is so essentially what they do is to use the stability estimates to show that the gradient converges strongly up to parabolic perturbation. Okay. But again, what I wanted to stress is that this doesn't work when you want gamma to infinity because this here blows up. So you need a different strategy to prove the incompressible limit. Okay. So I should have enough time to at least give you the idea. And I will show you the limit, but for a structured model. So when we have two species, we are describing the interaction between, for instance, healthy tissue and tumor growth. But if we want to describe the heterogeneity of the tumor, so the fact that tumor cells can have very different phenotypes, then what we do is we take a phenotypic trait, so a continuous variable y, which belongs to the interval 0, 1, and we want to describe infinitely many species. So instead of two species, we have a continuous species, and so now n depends on the phenotypic variable here. Okay, so ny at space x and time t describe the density of the species at phenotype y. Okay, and they evolve with the same equation. So where I have Darcy law, but now so now the pressure is again a power of the total density, which I call rho, and the total density is the integral between 0 and 1 of all the phenotypes. Okay, so essentially, rather than having the sum, I have the integral of all the phenotypes. And again, the reaction G, which depends also on the phenotype, is decreasing with respect to the pressure, as always. Okay, as before. So in this, so what I could show is that in fact you can pass the limit gamma to infinity. Okay, and there exists a triple. Well, actually, is just one function, and then the others are function of n. But there exists an infinity, rho infinity, and p infinity that satisfy the limit problem. Okay, and also the pressure satisfies the complementarity relation. So this is the relation that gives you the elliptic equation that is solved by the pressure where p is positive. So you will have that when p is positive, p infinity, this is 0. And so this links the problem to the free boundary problem that I was talking about before. Okay, so just to mention a couple of results. So the strategy is actually adapted from the one by Liu and Su, where they have a two species system. Okay, they have a two species system, and they have also a bounded domain with Neumann boundary condition, and the reaction that do not depend on the pressure. They depend on some concentration of some other chemical, but they didn't depend on the pressure in that paper. Also, then Jacobs adapted the strategy, and I think it fits to show you what is the strategy, because it's similar to what we did for the inviscid limit, in fact. Because the reason again is that I cannot hope to find strong compactness of this quantity of each phenotypic density. Okay, and so what I really need is to find strong compactness on the gradient. Okay, so again, as before, and as I was trying to show you before in the result by Gviazda and Pertam, to find the strong compactness of the gradient using regularity is not possible, because everything will blow up. So we need another strategy, and this is similar to what we did in comparing entropy inequalities. Is actually very, very similar. So we take the equation and we integrate between 0 and 1 on all the phenotypes, and we obtain the equation on the total density. Okay, so this is the equation on the total density, and is again a porous medium equation. And then what we do here is, what do we know already is uniform bounds in L infinity. Okay, that gives me a weak star convergence in L infinity for both the density and the pressure. Then I have again a uniform bound of P in L2H1, which gives me a weak convergence of the gradient when gamma goes to infinity. Then I have also that dt rho is bounded in a negative Sobolev space, because as you can see here, you have a Laplacian here. And in fact, This you can write, so this will be the divergence of grad rho to the gamma plus 1. And I didn't write it here, but also this one is bounded in L2. Okay, so you have a control of dt rho in H minus 1. And now the compensated compactness tells you that if a quantity, so if you can control time shifts for a quantity, and for the other one, you can control them in space. So this is in fact rho times p, okay? I have time control on one quantity and space control on the other. Then I can say with compensated compactness that limit of the product is the product of the limit, weak limit, of course. So I also have this information. Okay, here I put it. The fact that also this is in L2H1 gives me weak compactness for the gradient of this quantity. Okay, simply by convexity, because this is a convex function of the pressure, and the pressure is converging weakly. Okay, this is quite technical, but just to show you that we have enough information to say that I can pass to the limit in the total equation. Okay, because here, so here I have weak compactness, and so I can pass to the limit in this term. And then I have compactness also for weak compactness for rho. So I can pass to the limit in here, although this R is the limit of R gamma. Sorry if I'm going back and forth. So I call this R gamma, okay? And it will have a weak limit R infinity, which for the moment I cannot identify. And the reason that for which I cannot identify this is that I don't yet have strong compactness of the pressure. So it will be some limit R infinity, but for the moment I don't know what it is. But this still is enough. I have this equation for the total density. So as before, I will use this to get the strong compactness of the gradient. So again, the goal is to get the strong compactness of the gradient of this power of rho. Okay. So the idea is similar to what I showed you before, even though there are some differences. So what I will do now is I test this equation against this difference. Okay. So I simply test, I integrate by parts, and I get this equality. I get this equality here, and what I want to show is that the right-hand side is small, once again. Why? Because if I do that, if the right-hand side is going to 0, as gamma goes to infinity, then I will have that the gradient converges, because I can rewrite this this norm as the sum of these terms simply by developing the product, okay? And so this is this left-hand side here that I want to show that goes to 0. And this one is already going to 0 because this is a fixed and this converges weakly, okay? So the final goal will be show that this right-hand side goes to 0 as gamma goes to infinity. Okay, so the first one is quite easy, this one here, because I have dt rho times rho to the gamma plus 1, and I can rewrite it, sorry. I can rewrite it, this first product, like this, okay? This is simply, so dt rho times rho to the gamma plus 1 is simply 1 over gamma plus 2, the time derivative of this power. And then I have dt rho times p infinity here. So the first one obviously goes to 0 when gamma goes to infinity, because I have 1 over gamma. And this other one also goes to 0. And again, the reason is that I have this, this relation between the final the final density and the final rho. Sorry, the final density and the final pressure. So I have that when P is positive, rho is constantly equal to 1. Okay. So just to give you the idea, so if your pressure is something like this, okay, if this is your pressure, then at infinity, then your equation will look something like this. So rho infinity is actually equal to 1 in here. Okay. So it's constantly equal to 1, and so this will vanish. No, sorry, what did I say? Yeah, exactly. Yeah, this is true. So this is constantly equal to 1. I mean, this is constantly equal to 1, and it's vanish. Okay. Okay. Then I have only the reaction that remains. And as before, the reaction is a bit technical, but the idea is to use monotonicity. So I want to show this goes to 0. I don't have enough compactness, but I can use monotonicity. So I add and subtract G of P infinity. And then I have two terms. So I have the one with the difference between the G, and I have the one with G of P infinity. Okay. So here I want to use monotonicity. So I do, again, another trick. I do plus minus P gamma in here. And so what I have that the first product, so I take these two together. And this, again, is always the same trick. I collect P gamma in here, and this is P gamma times rho minus 1. Okay. Yes, exactly. Okay, and again, this in the limit is equal to 0. So I will have that this integral converges to 0. This is, again, is not, here I'm hiding something under the carpet because it's a bit more technical than this, but the reason why this integral goes to 0 is, again, the saturation condition. Okay. And then I have the other one, and here I simply use monotonicity. Monotonicity because I have this difference, and this times this difference, and G is decreasing. Okay. So for the blue term, I'm fine. It's going to 0. And the other one, well, now is much easier because this is fixed. Okay. And then I have N times this difference. And again, I can use compensated compactness to prove that the product of the limit is actually the limit of the product. And this here is converging to P infinity weakly. The reason, again, is that rho to the gamma plus 1. So rho to the gamma plus 1 is actually, so is again rho times P, right? And so it's converging to rho infinity times P infinity. But again, this is equal to P infinity. Again, for the fact that rho is 1 when P is positive. So the reason is that any power, gamma plus anything, in the limit, it would still be the pressure because gamma is very, very large. Okay. So this also goes to 0. So essentially, long story short, I can pass to the limit and I can prove that the gradient converges strongly. So this was the whole point. I wanted to prove that the gradient converges strongly. And then, okay, simply thanks to this, I have also strong compactness of this quantity by Poincaré inequality. Same for the pressure. And so I can identify the reaction. So finally, I can actually say what R infinity is. And finally, I can find also the equation for the pressure, because if I test this equation on rho by rho to the gamma plus 1, I obtain an equation for rho to the gamma plus 2, which again is converging to the pressure. So this is converging to the pressure. This is converging to the Laplacian of the pressure. And this is 1 over gamma, so it's converted to 0. And I have the complementarity relation here. Okay. So, yes, just to conclude, what I showed is, first of all, the inviscid limit. So from Brinkman to Darcy, then the incompressible limit from a Darcy model to a free boundary problem. But what I didn't mention is that for incompressible limits, there is also the limit in, from the Brinkman model. So you take p equal to n to the gamma, and you can pass the limit in here. And this was done a few years ago. And now to complete the pictures, there is some work to be done, because we don't actually know, for instance, if we can pass the limit in here. So from nu to 0 in the two free boundary problems, and if this gives the same solution here. And also we don't know much about the rates. There is some result for this limit, but all the rest is completely open. So sorry if I was too long. With this, I conclude. Thank you for your attention.
Thank you for the excellent presentation. Does anyone have any question?
Thank you for the nice talk. I was just curious about, at the very beginning, you said something about the two species, if they start to have disjoint supports, that they always have disjoint supports or something. I was just curious if this is easy to see from the equation, and if this also translates to this continuous phenotype.
Oh, yes. So it's a very good point, in the sense that for the phenotype, I don't know. So sorry for this. For the phenotype, it's difficult to say, because now we have a continuum. Okay, so for the first question, you can see it from the equation, because they have the same velocity field, right? So you have dt n1 minus divergence n1 grad w equal to reaction, and the same for n2. And so if you think about for particles, okay, for instance, this can be approximated with a particle system through the mean field limit. And if you think of two particles, and of n1 and 2, that they get in contact in the regions of where I have the interface, they will not mix, because the gradient is the same. So they will follow the same velocity field. They will not, I don't know if you also see me, because I'm making hand gestures, but they will not cross. They will just continue in the same direction, so they cannot intermix, okay? For the phenotype is more tricky, because you don't really, how do you define segregation initially? You don't have, because for instance, n1 and 2, you have n1 times n2 equals 0, x and t, almost everywhere, for instance. This is a way of saying they are segregated. For the phenotype, it's different, although I know of papers where they consider a similar equation, and they studied in a formal way, with a formal analysis, but they study the behavior when t goes to infinity. When you have some rescaling, now I don't want to be mistaken, but I think the rescaling is putting an epsilon here, and then plus epsilon square second derivative with respect to y. So this would mean that you have changing of phenotype, random changing of phenotype, okay? And if you put the right scaling, which I hope it's right here, when time goes to infinity, and so you rescale also time here, you can actually see the selection of phenotypes. So you can see that for each space and time, X and T, you have a Y bar of X and T for every, so you have only one phenotype for every X and T. This you can see, but I think you really need a rescaling, a particular scaling, and you can only see it for time long, at least as far as I know. But there is a, yes, there is some, I mean, it's not trivial, and there are people studying that. This I'm
Okay.
sure.
Thank you very much.
Thank you for the question.
Another question? And the people from the chat? No. I have a question, probably is a naive one. It's about the first part that you talk, the strong compactness.
Yes.
You said the entropy of the final point, nu zero, is bigger
Yes.
than. Can you explain this again, please?
Yes, absolutely. So here, because actually what I didn't say, so there again, I was hiding under the carpet, that I have weak convergence of this quantity in L1. And so I use the fact that I have a lower semi-continuity of H, because H is a convex functional. So I have that the limit of this will be less or equal than, no, sorry, the inverse. Okay, and so I have an inequality for when I pass to the limb soup. Okay, but to show what I didn't really say is that I need to prove that this converges weakly. So this is in L1 of RD. And we have everything we need to show that this is true, because we have that the quantity for each time they are in L infinity, L1, and I have control of second moment. I don't know if this answered the question.
And another thing is about the convergence. You have some text to estimate as if to the second part. When you send the gamma to infinity, you have some estimate the relation between your solution of the problem gamma and gamma equals infinity. You have some estimate?
Yes, you mean of the rate?
Yes.
Yes, we have some estimate of the rate, which are actually quite interesting. So, where is it? Okay. So what we can say, so the interesting thing is that this limit, I show you the slide with the long literature state of the art, was very, very studied, but there was little on the rate that was known on the rate. And the only result we knew was by Alexander. So it's Alexander, Kim and Yao, 2014, I think. So what they have is that the two Wasserstein distance between n gamma and n infinity, you can estimate it with a polynomial rate, which is of 1/24. So actually it was what they say in the paper is that is really non-optimal. It's quite small. And so we were motivated by that with Thomas Dumbietz again and Benoit Pertam. And we studied it, but in H-1. So what we prove is that the H-1 norm, again of n gamma minus n infinity, actually the homogeneous one, we could find a rate that is of like this, goes like the square root. So it actually improves some way this result. But again, we think it's not optimal. We think maybe a C over gamma could be optimal. C is just a constant, okay? So I can just put 1. But we think it's not optimal. And there are a lot of questions here. For instance, what is the rate of the pressure, because we only know the rate for the density, but not for the pressure, which is much more difficult because the pressure itself is the n to the gamma, and gamma is goes to infinity. So it's much more difficult to quantify. But at least we have this quantification here, let's say, this estimate, yes.
Thank you again for the excellent presentation. Let's say thanks to Noemi again.
Thank you. Thank you very much. Thank to you and Eugenia for the invitation. And I wish you a nice afternoon, I guess, in Chile.